Okay, in this video, we are going to discuss how we can deduce structural information based on fragmentation peaks. So previously, we have mentioned that the molecular ion is formed when a beam of electrons hits the molecule, leading to the removal of an electron and thus forming a cation radical. However, this molecular ion does not tend to persist very long in a mass spectrometer. Instead, the molecular ion tends to undergo fragmentation to form cations that have a smaller MZ value, accompanied by the formation of a neutral species, which could be a radical or a small molecule such as carbon monoxide. Okay, so for example, this molecular ion corresponds to pentane, C5H12, and the MZ value over here is 72. So a fragmentation process can occur where this CC single bond is broken, leading to the formation of this carbocation, which has an MZ value of 57, along with the release of a methyl radical. So therefore, what this tells us is that in the mass spectrum of pentane, the molecular ion peak is at MZ72, but we will also see a significant peak at MZ equals to 57. And of course, this peak or this cation that is MZ57 can undergo further fragmentations. So we will expect to see peaks that have an MZ value that is below 57 as well. Okay, so fragmentation processes tend to favor the formation of stabilized cations. Okay, in the subsequent few slides, we will discuss what are some factors that stabilize cations. And you also need to be aware that the fragmentation might also be accompanied by what we call rearrangements. Okay, why do we need to know this? Because what happens is that for certain functional groups, they all fragment in a similar way. So fragmentation patterns with the loss of certain groups are characteristic of particular structures and functional groups. So we can then use the mass spectrum to figure out what functional group is there, what groups has been lost, and we can attribute the peaks at certain MZ values to certain cations. Okay, so now in the next few slides, we'll discuss three common fragmentation patterns. The first one is when there are bonds adjacent to carbonyl groups. Okay, so carbonyl groups are found in compounds such as ketones, aldehydes, but also carboxylic acids, esters, amides, acyl chlorides. Okay, so bonds next to carbonyl groups are readily broken in MassSpec because when the bond is broken, it forms an acylium cation. So acylium cations have a general structure of RCO+, and this is stabilized by resonance. Okay, what this means is that, for example, aldehydes, they can cleave either the CH bond or the CC bond to produce either of these two carbocations. And these carbocations are resonance stabilized because the p orbital on C overlaps with the p orbital on O, and this allows the positive charge to be delocalized between both carbon and oxygen atoms, which makes this carbocation more stable. Okay, and similarly, carboxylic acids can also undergo such bond cleavage to produce the same acylium cation with the release of a hydroxyl radical. Okay, so basically for aldehydes, we will expect to see peaks that correspond to M-1 due to the loss of a hydrogen radical, as well as a peak at MZ29 due to the HCO plus cation. Okay, and for carboxylic acids, we will see a peak that corresponds to M-17 due to the loss of a hydroxyl radical. Okay, the second case is bonds adjacent to heteroatoms, and these heteroatoms includes oxygen, nitrogen, and rarely sulfur. Because again, when you cleave the bond next to a CO, or when you cleave a CC bond next to O, N, or S, the resulting cation is stabilized by resonance. So for example, in an alcohol, when I break this bond, I release an alkyl radical and I leave behind this carbocation where I can delocalize the positive charge onto the carbon. So again, this is an example of resonance stabilization because the positive charge is so-called shared amongst the carbon and the oxygen. So the positive charge is not just solely on oxygen. It can be delocalized onto carbon, and this increases the stability of this carbocation. Okay. Lastly, when we have compounds with benzene ring, or not just benzene ring, but a benzyl group, which is C6H5CH2, the CX bond tends to cleave very easily. The X will become a radical, and C6H5CH2 is left behind as a benzyl carbocation, which is also stabilized by resonance. And furthermore, the benzyl cation can rearrange into a tropylium cation, which is even more stable because the tropylium cation regains the aromatic stability that is associated with the benzene ring. Okay, so what this means is that in compounds with such a structure, it can be C6H5CH2Cl, C6H5CH2OH. We will often expect to see peaks at MZ91, which can correspond to the benzyl cation or the tropylium cation. Okay, so over here I have an example which is C6H5CH2Br. The first thing we notice is that the M peak is at 170. There is M plus 2 peak at 172, and these two peaks are at their intensities are in a 1:1 ratio, which is what we predict based on the isotopic abundance of bromine 79 and bromine 81. Okay. Secondly, the base peak occurs at 91. There is a loss of 79 due to the cleavage of the CBr bond. The bromine is released as a radical, so what is left behind at MZ91 is the C7H7 plus cation, which could correspond to the benzyl cation or the tropylium cation. Okay, so now can you take some time to attempt example 2? Will be quite challenging, so just try our best to figure out the structure based on the two spectra you are given.